This video, we're going to prove the following fact. All groups of order 9 are abelian. If you like seeing mathematical proofs, you should seriously consider subscribing to my channel, as that's what we do here. We prove mathematical facts at all levels. Now, when it comes to this fact, I'm pretty much going to just sketch the proof. I'll prove part of it, but it's just too long and tedious to prove the whole statement. Having said that, let's get into it. Now, suppose there exists an A and G where the order of A is 9. That is, the generator of A is G. Because G also, let G be a group. G is a group. Okay. Now, if G has an element whose order is the same as the order of G, then that element generates G. Okay. So, what does that tell us? Oh, if you have a generator, that implies that G is cyclic. Okay, so let's suppose that no element is of order 9. Now suppose for all, let's call it G. For all G in the set G, the order of G is less than 9. That is, the generator of all G's are a subset, a proper subset of G. Now, G has a non-trivial subgroup if and only if the order of G is prime, has no non-trivial. But the order of G is 9. That implies that G does have a non-trivial subgroup. A trivial subgroup is the subgroup that just contains the identity element, and the other subgroup is the group G itself. G is the subgroup of G. Okay, so this has a non-trivial subgroup because the order of G is not prime. Now, by Lagrange's theorem, we have that G does have a non-trivial subgroup H. We know that the order of H must be 3 because Lagrange's theorem tells us that the subgroup must divide the order of the group. The only number that divides 9, or the only numbers that divide 9 are 1, 3, and 9. And 1 is just a subgroup that has the identity, and 9 is the whole group G, so the only non-trivial subgroup is of order 3. Of order 3. Suppose H is equal to E, A, and B. That tells us that the order of A is 3. Because A is not E. That means the order of A is at least 1. But the order of a group or subgroup must divide the order of, in this case, the subgroup. It must divide 3. The only numbers that divide 3 are 1 and 3. And I'm saying that A is not 1. Sorry, the order of A is not 1. The only element in a group that has order 1 is E. Okay, the order of A is 3, and the order of B, you know, I take that back, shucks. How about we say A and A squared? I apologize. H is equal to A and A squared. Now, since H is a proper subset of G, there must exist some elements in G that are not in H. Call one such element B. Okay, so now B is in G, but G is closed. That implies that B squared is in G. That actually implies that 2B cubed is in G. But the order of B, since B is not E, the order of B is 3. Okay. Now, call it set S. Now, S is equal to E, A squared, B, and B squared. Now, I want to build up to G. Now, B can't be E, and if B squared is E, since the order of B is 3, B must be E. Can A equal B? Well, no, I picked an element B that wasn't in H. There exists some element in G that are not in H. So B is not one of them. Can A equal B squared? No, it can't equal B squared either. So these are 5 distinct elements. And if I were to multiply the right sides by B, this side will become B cubed or E. And that means that B would be the inverse of A. But the inverse of A is A squared. And I picked B squared to be different from A. And the only way that I could be wrong is if B is equal to A squared. And no, it isn't. B is different. Okay, those 5 elements are different. Now, I claim that G is the set that has E, A squared, B squared, AB squared, because I have to be able to multiply A and B. Of course, A could have been one of the elements in set S, but I'm going to show that's not true. A squared B and A squared B squared. First, let me show that these are all different. AB equals to AB squared. That would I kill off A on the left, I kill off a B on the right, and I get that E equals B. No. B and E are different. Can AB, so AB can't equal that. Can AB equal A squared B? Well, same argument. Kill off an A on the left, kill off a B on the right, we get that E equals A. If A squared equals to A squared B, then E equals A. Another way to show that is as follows. A squared is A times B. Say AB is equal to something times AB. That means that's E. So that's not true. Now we have that AB, we're considering this. Well, if I kill off an A on the left and a B on the right, the left side is E, kill off an A on the left, I get AB is equal to E. If I multiply both sides on the right by B squared, that's E. So I get A times E, and here I get B squared. No. They're different. These elements are different. A does not equal B squared. Okay, so we dealt with AB. Let's look at AB squared. Can AB squared equal to A squared B? Well, let's kill off an A on the B, an A on the left, and a B on the right. A on the left, and one B on the right. So we get B equals A. Nope. We know A and B are not equal. Can AB squared equal to A squared B squared? Well, I would kill off B squared on both sides and say A equals A squared. No. And if you didn't like that, kill off an A here, kill off an A here, and you get A and E being equal. That's not true. A was different than E. A was different from E. Now let's deal with A squared B squared, or A squared B, excuse me. So I just have to show that A squared B equals A squared B squared is a problem. Well, the right side is A squared times B times another B. I'll bracket up this way. And the left side I'm not touching. Oh, say A squared B is equal to itself times B. That would imply that B is E. But that's a contradiction. Okay, so basically what I showed is, let's put the red underline back. What I underlined, those elements are all different from one another. Now, you can argue, and I may not do this, you can argue that these five elements are different than these four elements. And you can show that. I mean, can E equal AB? Well, if I multiply by A inverse on both sides, this is E. E times B is B, just B. And you don't need E. A inverse times E is A inverse. But A inverse is A squared. And how many times can I say these are different? I'm telling you they're different. A and B are different. And that means that A and B squared are different. And that A squared and B are different. We proved that. So that's how you can prove, for example, E does not equal AB. Can E equal A squared B? Well, I'll multiply this by A. This was E. I multiply by A, I get that. I multiply this by A, that gives me a cubed, which is e times b. Gives me a equals b. And if you went through all of these, that is, if you check that e can't be ab, and e can't be this, and e can't be that, and e can't be this, and a can't be ab, and a can't be ab squared, etc. And then you show that a squared can't be ab, and a squared can't be that or that. You went through all of them. I guess there's 20 combinations. Then you will know that that's a G, because any 9 elements in G that are distinct make up G. Okay, so now why is this group? So now we have the group. This is the group. Okay, this is the only group of 9 elements that doesn't have a generator. This is it. Now, why is this group abelian? Well, I just have to argue that BA can only be AB. So, can BA be E? Can BA be A, the second element? Can BA equal A squared? Can BA equal B? Can BA equal B squared? Can BA, well, we'll skip AB. I'm going to show that it can't equal any of the others, so it has to be AB. Can A squared, BA, equal AB squared? Can BA equal this? And lastly, can BA equal this one? Alright. For the first one, if I multiply it on the left by B squared, this is E, because it's B cubed times A, that's A, and then the right side is B squared times E, which is B squared. No. So, BA cannot equal to E. What about BA equaling A? Well, if you multiply something by A and you got A, then B equals E. But that's a contradiction. B and E are different. Here, on this one, if I killed off an A on the right side of each side of the equation, I get B equals A. But that's not true. If you multiply B by something and you get back B, that implies A is equal to E. No. BA is equal to B squared. I'll write B squared that way. Cancel off B on each side. A equals B? No. Doesn't happen. Remains to show these 3 statements are not true, or can't be true. If I take the inverse of both sides on this equation, I get that A inverse B inverse is equal to B inverse times A squared inverse. But A inverse is A squared, B inverse is B squared. B inverse is still B squared, and A inverse squared is A. Keep the left side the same, but this here is B times BA, where BA is A squared B. So we have B times A squared B. This is equal to A squared B squared. Now, we kill off for B on the right side, on both sides of the equation. And we get A squared B is BA squared. But A squared B is BA. So BA is equal to B times A times A. So BA is equal to BA times something. That means that something is E, but A and E are not equal. That is, BA cannot equal to A squared B. Let's try the middle equation. Again, if we take inverse of both sides, we'll get the following. A inverse, B inverse is B squared inverse A inverse. A inverse is A squared. B inverse is B squared. B inverse squared is B, and A inverse is A squared. Okay, now I'll write the right side as BA times A. Left side I won't touch. But BA, according to the top, is AB squared times A equals A squared B squared. On the left-hand side of both equations, I'll kill off an A. So I get this. But AB squared is BA. So BA, I'll write this as B times BA. Well, if BA is something times BA, that something must be E. But that's a contradiction. Contradiction that BA equals AB squared. That's not possible. Okay. In this equation, on both sides, I'm going to multiply on the left by A and the right by B. A, B. This becomes AB squared. And this is E times E, which of course is E. But the order of AB can't be 2 because 2 doesn't divide 9. Well, what divides 2? 1 divides 2 and 2 divides 9. That is, AB must be E itself. AB is E. That means A is the inverse of B, but B inverse is B squared. And no. A and B squared are not the same. They are not the same. This here is a contradiction, and it contradicts the top line. BA cannot equal to A squared B squared. So what we concluded is that BA is not an element of this set. The set that contains E, A squared, or B, B squared, AB squared, A squared B, or A squared B squared. 1, 2, 3, 4, 5, 6, 7, 8. There's only one element that's in G that we didn't list, and that element is AB. And since B is in the group and A is in the group, BA is in the group, and it must equal to AB. That implies G is abelian, and that implies that all groups of order 9 are abelian. And that completes the proof. If you're into watching mathematical proofs like this, subscribe to my channel. Please click the like button. Tell your friends, family, and enemies about my channel. See you guys in the next video. Watch and learn.